Hello, good evening. I am Saurabh and I welcome all of you to this session of Applied Thermodynamics. In today's session, we will discuss something related to internal combustion engines. We have been discussing internal combustion engines for last few weeks. We have solved some questions, discussed some concepts. So that discussion and solving those questions we will continue in this session as well. Okay. And I hope that this session will be helpful for you in solving your assignment problems. Okay, so we will begin our session. Okay, so let us begin with question number 1. Question number 1 says that by higher octane number of spark ignition fuel, it is meant that fuel has. So there are some properties given as options. So higher octane number means what? We have studied that fuels for spark ignition engines have a quality called octane number. Okay, so octane number basically uh, tells about the ability to resist the auto ignition. Okay, the resist the knocking. Okay, so the fuels which have higher octane number, they they will not easily undergo knocking. Okay, so knocking happens because of auto ignition. Okay, so the fuels which have higher octane number, they will not easily undergo knocking, or they will not easily undergo auto ignition. So we will check all these options one by one. Option A, it says that fuel has the fuels which have higher octane number that have higher heating value. No, octane number has nothing to do with heating value, right? So option A is not correct. Higher flash point, this is also not correct. Part C says lower volatility, and last part says longer ignition delay. So as we discussed that octane number is something which tells about how much fuel is resisting the auto ignition. The fuels which have higher octane number, they will not auto ignite easily. So in other terms, you can relate this thing to the ignition delay. Okay, the fuels which have higher octane number, they will have longer ignition delay. Okay, so I hope that you will be able to answer. That correct part should be part D, last option. Okay, so we will move to the question number 2. Question number 2 says isooctane C8H18, it is burned with 120% of theoretical air in an automobile engine. The molecular weight of fuel and air are 114 and 29 respectively, and we have to find the equivalence ratio. Okay, so it is given that this fuel is burned with 120% of theoretical air. So theoretical air, what is meant by theoretical air? So theoretical air is basically the quantity of air which is required when fuel burns in stoichiometric nature. Okay, so stoichiometric means that there is just enough oxygen for the complete combustion. Okay, so there is no leftover oxygen in the exhaust. Okay, for example, if there is one carbon atom, then for complete combustion you will need two sorry one oxygen, right? So you will get CO2. Okay, so this is complete combustion and there is no leftover oxygen in the product. Okay, so this is basically what is uh, we call stoichiometric equation. So this is theoretical air. Of course, there will be some nitrogen 3.76 N2. Okay, so this is theoretical air. Okay. So in this question, it is given that this fuel is burned with 120% of theoretical air. So this means there is 20% extra air, right? And we have to tell the equivalence ratio. And what is equivalence ratio? So equivalence ratio is basically the ratio of actual fuel air ratio to the stoichiometric fuel air ratio. Okay, or you can write it as air fuel ratio. Air fuel ratio is basically just reciprocal of fuel air ratio. Okay, here we have written fuel air ratio. Now I am writing air fuel ratio. So we have just reciprocal. Okay, air fuel ratio in stoichiometric condition to the air fuel ratio in actual case. So this is basically equivalence ratio. So equivalence ratio will tell that how much extra fuel is there. Okay, if it is greater than 1, if the equivalence ratio is greater than 1, so this means you have more fuel or less air. Okay, and if equivalence ratio is less than 1, this means that you have less fuel and more air. So less air, sorry, more air means lean combustion. Okay, so in this case, you have 120% uh, theoretical air. So this means 120% of theoretical air. So this means you have 20% extra air. So basically here lean combustion is taking place. Okay, so you can calculate the fuel air ratio in the actual case, which is 120% here, and you can find the fuel air ratio in the stoichiometric case. But here you have to find the equivalence ratio. For that, you don't need to calculate all these things. You can easily answer that it is 120% of theoretical air. So you can just take the ratio 100 to 120%. So whatever you will get, that will be your answer. But just for practice, we will calculate all these ratios. Okay, so sorry. Okay, E8 H18, there will be some air. Air is O2 plus 3.76 N2, and after combustion you will get carbon dioxide. Okay, there will be some H2O. If there is more air, so there can be some leftover oxygen and some nitrogen. Okay, so we don't know how much air is used. Let us say we don't know the amount of air that is being used. So let us say it is X air and some CO2, some H2O, some O2 and some N2. Now let us try to balance the carbon atoms, number of carbon atoms. So on left hand side you have 8 carbon atoms. So on right hand side you should have 8 CO2. Okay, you have 18 H. So here there should be 9 H2O. Okay, so hydrogen will also be balanced. On left hand side you have 2XO, right? Number of oxygen atoms is 2O. So the number of oxygen atoms on the right hand should also be equal. Okay, so how many oxygen atoms are there? 2 into 8, so 18 here and 9 here. So you have 16 plus 9, 25 oxygen atoms are there, and you had x, so x minus 25. Here it was 2x divided by 2. Okay, correct. And nitrogen, let us say nitrogen is not reacting and there's no NOx formation. So whatever nitrogen was there, so all the nitrogen is coming out and there's no NOx formation. Let us assume that. So you will get 3.76 x N2. Okay, so this is our balanced equation. Okay, for stoichiometric case, there should be no leftover oxygen, so this quantity should be 0 for stoichiometric case. Okay, but since in this given question there is 20% extra air, so there will be some leftover, oxygen. Okay, so for stoichiometric case, let us say if you have to calculate the fuel air ratio for the stoichiometric case, then just make this quantity 0. So you'll get 2x is equal to 25 or x is equal to 25 by 2. Okay, so mass of fuel is mass of fuel is molar mass of fuel into number of moles of fuel. So here it is 1. Okay, mass of fuel, and mass of air, it is x into whatever. Okay, and for actual case, this thing will not be 0 and you will take x 120% of x that was in stoichiometric case. Okay, so this is how you will calculate the fuel air ratio or air fuel ratio in both actual case, in actual case as well as in stoichiometric case. Okay, and then you can take the ratio of these two quantities, so you'll get the equivalence ratio. But for solving this question, you don't need to find all these things. You just take whatever fuel is there. Let us say there is uh, some mass of fuel. Okay, and there is some mass of air in stoichiometric case. Okay, and some mass of air in actual case. So mass of air in actual case is 120% or 1.2% of mass of air in stoichiometric case. So if you want to take the ratio of fuel air ratios, then you will get mass of fuel divided by mass of air actual to the mass of fuel by mass of air stoichiometric. So these two quantities will cancel out each other. So whatever you will get, that will be mass of air in stoichiometric to the mass of air in actual. Okay, so 100 divided by 120. So if you calculate this quantity, let's calculate this quantity. 100 by 120. So it is coming around 0.833. Okay, so among the given options, the part B 0.83 is the closest value. So this should be the correct option. Okay, so I hope these terms are clear. The equivalence ratio or air fuel ratio or fuel air ratio, the excess air. What do you mean by lean combustion? Okay. So lean combustion mostly takes place in CI engines. In diesel engines, the nature of combustion is lean combustion. Okay. So there is some extra air. Okay. So if it is clear, then we will move to the question number 3. Question 3 says the specific fuel consumption BSFC of a diesel engine is 0.3 kilogram per kilowatt hour. The calorific value of diesel is 20 megajoule per kg. So we have to find the brake thermal efficiency. Okay. There are few terms. We will discuss them first. Brake specific fuel consumption. So when we say this term brake, so this means whatever you are getting at the shaft. Okay. So we know that there is some indicated power, that is the theoretical power that you are getting, but there are some friction losses. Okay. So when you subtract those frictional losses from the indicated power generated, then you will get the brake power. Okay. So brake power is basically the indicated power minus friction power. Okay. Friction power is basically loss due to the friction. Okay. So brake specific fuel consumption is the amount of fuel per unit brake power. Okay. So brake specific fuel consumption is mass of fuel required to produce 1 unit of energy at shaft. Okay. So here it is given 0.3 kilogram per kilowatt hour. So it means that you are using 3 kilogram of diesel for producing 1 kilowatt hour energy. Okay. And brake thermal efficiency we have to find. So brake thermal efficiency neta is equal to brake power, whatever you're getting, divided by chemical energy of fuel consumed. Okay. So for 1 kilowatt hour, so 1 kilowatt hour means the amount of energy 1 kilowatt hour is the amount of energy that will be produced in 1 hour at the rate of 1 kilowatt. Okay. So 1 kilowatt into these much seconds. Okay. Or you can say write it as 1 kilojoule per second into this. So it is equal to 3600 kilojoule, right? Correct? Or you can write it as 3.6 megajoule. Okay. Okay. So in this question, it is given that BSFC or the brake fuel consumption is 0.3. Okay. So 0.3 kilogram for 1 kilowatt hour. Okay. And 0.3 means how much energy? Just multiply with the calorific value of the fuel. Okay. The calorific value is given to be 20 megajoule per kg. Okay. So if you multiply this quantity by 20, you'll get 20 into 0.3 megajoule. Okay. So this much is the chemical energy in the fuel. If you calculate this value, it will come out to be how much? 6, 6 megajoule for 1 kilogram of fuel. Okay. Not 1 kilogram for fuel. It is for 0.3 kilogram of fuel. And how much energy we are getting at brake or the shaft? We are getting 3.6. Okay. So you can calculate the efficiency. It will be 3.6 megajoule divided by 6 megajoule. So just find this ratio. 3.6 divided by 6. So it is coming out to be 0.6. Okay. In terms of percentage, it will be 60%. Okay. So if you check the options, then option A, 60%. So option A should be the correct option. Okay. So if it's clear, then we will move to the next question. Question 4. It says that a 4-stroke engine having 4 cylinders. Okay. 4 cylinders have cylinder diameter of 40 mm. Cylinder diameter of 40 mm. Cylinder diameter is also called bore. Okay. So bore is 40 mm. And stroke length is 70 mm. Clearance volume is given to be 2000 mm cube. We have to find the engine capacity in cc. Okay. So engine capacity is basically the swept volume. Okay. In cc, many times you might have heard that this motorcycle is 200 cc motorcycle or something like that. Okay. So that cc is basically cubic centimeter. Cubic centimeter. And that represents the swept volume. Okay. This engine capacity is basically the swept volume. This is not the total cylinder volume. Total cylinder volume is equal to swept volume plus clearance volume. Okay. So when you are talking about engine capacity, it is just the swept volume. Okay. So in this question, there is no role of this clearance volume. Okay. So we don't need this quantity. We need to just calculate the swept volume. So how will you calculate the swept volume? It is just the volume of the cylinder, and not the total volume of the cylinder. It is just the swept volume. So swept volume for one cylinder, let us calculate first. So it will be equal to what? Pi by 4 into diameter square into stroke length. Okay, so pi by 4 into cylinder diameter is 20 mm square into stroke length is 70 mm. Okay, so this will be the swept volume of one cylinder, but it is given that this engine is four cylinder engine, so there are four such cylinders. Okay, so the total swept volume, to calculate the total swept volume, we need to multiply this quantity by 4, equal to 4 into pi by 4 into 40 into 70 mm cube. Okay, so if you calculate this value, then we will get how much? 70. So I am getting 8, 7, 9, 6 mm cube. So if you want to convert this quantity into cc, then you need to put the correct value. Right, is the correct value 351.86 into 10 to the power 3 mm cube. Okay, so if you want to convert this quantity into cc, then you just need to divide this thing by 1000, so you'll get 351.86 centimeter cube or cc. Okay, 351.86 cc. Okay, so this will be the engine capacity. So if we check these options, then option A is 300, option B is 352. So yes, 352, it is the round off value. So this is the closest one. So part B should be the correct option. Okay. So I hope it is clear what do we mean by engine capacity. It is basically the swept volume, total swept volume. If there is one cylinder, then you can just use this pi by 4 into bore square into swept stroke length. And if there are more than one cylinder, then you just need to multiply by the number of cylinders. Okay. So if there is no doubt, then we will move to the question number 5. Question number 5 says that in order to eliminate knocking in compression ignition engines or CI engines, there should be short delay period for the fuel. So first, let us try to understand what the question mean. Short delay period means ignition delay. Okay, short delay means short ignition delay. So what happens in diesel engine? You know, the basic uh, principle how the diesel engines work. You know that in intake stroke, the air is coming inside the cylinder, then this air is compressed, then then this air becomes very hot, and this hot air, the fuel is injected in the form of spray. Then this fuel starts burning. Why? Because it is injected in hot environment. Okay, so auto ignition. But it is not like that you are injecting the fuel and it is immediately burning. There is some time difference when you start injection and the starting of combustion. There is some delay, so that is the ignition delay. Okay, so what will happen? uh, Let us say you have, this is the mass of fuel injected and this is the time you have started igniting. Let us say just you are continuously injecting. Okay, so initially there will be no combustion, right, because of ignition delay. So whatever fuel you have injected inside the chamber combustion inside the cylinder, so that is unburnt. Okay, then after ignition delay, period, there will be a start of combustion. And when the combustion is starting, so there will be some fuel which has already been injected, and that would have formed some mixture with the air. So all that fuel which has already been injected, that will suddenly burn. Okay, so there will be sudden pressure rise, sudden temperature rise. So that will lead to the knocking. Okay, so if you want less knocking, if you want to eliminate the knocking, then this ignition delay period should be less. Why? Because if the ignition delay period is less, so there will be less time for the fuel accumulation. Okay, so there will be less formation of fuel air mixture. Okay, so there will be less knocking, or you can even eliminate the knocking. Okay, so if you want to eliminate the knocking, then the ignition delay should be reduced. Okay, so the option A is correct, true, right? So we want short ignition delay to reduce the you know knocking. uh, what else we can do is that we can inject less fuel before the start of ignition. Okay, and when the ignition has started, then you can increase the quantity. So what will happen uh, when the combustion will start? So there will be less fuel inside the chamber, and there will be lesser pressure and temperature rise. And you don't want sudden pressure or temperature rise, because it will lead to noise, knocking, and NOx formation, right? Because that NOx formation takes place at higher temperature. Okay, so the profile of fuel injection can be something like this. You are injecting less fuel, then you can increase the quantity of fuel injection. Okay, so here let us say combustion is starting, and there this is your ignition delay. Okay, so whatever fuel has been injected in this location, that will result in sudden pressure rise, sudden temperature rise, because of sudden combustion of fuel air mixture, which has already been there before the start of ignition. Okay, so here the start of ignition. Okay, so you can have this type of fuel injection profile in order to reduce the knocking or NOx formation or noise. Okay, so I hope this is clear, and we can move to the next question. Okay, question 6. Question 6 says the exhaust gases leaving the combustion chamber of SI engine, spark ignition engine, contains about how much ppm of HC? HC is basically hydrocarbon, unburned hydrocarbon, components equivalent to 1 to 1.5% of fuel. So you know that in the exhaust there is some unburned fuel. Okay, and SI engines are anyway they work in rich region, right? Either stoichiometric, or there can be some extra fuel. So there will be some unburned fuel, and because of that there will be some unburned hydrocarbon. Okay, so that unburned hydrocarbon will come out from the exhaust. So it is asking that how much HC is there, and that HC is something around 1 to 1.5% of the fuel. So we have to tell the order of ppm. So here the correct option is part A. It is around some 6,000 parts per million ppm. Okay, HC is basically Hydrocarbon ppm is parts per million. It is just a unit of concentration. Okay, so if this is clear, then you can move to the question number 7. Question number 7 says that the maximum NOx is oxides of nitrogen. There are many different types of oxides, and all those oxides are combinedly called NOx. So X can be some number, 1, 2, or whatever. It's formed at slightly lean equivalence ratio at which flame temperature is very high. So you know how this NOx is formed. Even if there is no nitrogen in fuel, but still NOx is formed. So this nitrogen is actually already present in the air. Okay, N2 is there in air, right? Something around 75% air is basically nitrogen. Okay, so this nitrogen is in molecular state, and there is triple bond between two nitrogen atoms, and these triple bond are quite strong. Okay, they will not easily break, but at very high temperature this bond can break, and you will get you know nitrogen radicals. Okay, so they can form the NOx. So this NOx formation takes place at very high temperature, and the mechanism for NOx formation is called Zeldovich mechanism. So this is one of the very popular mechanism to understand how this NOx is being formed. Just check the spelling of Zeldovich. I don't know if there is some H. And this takes place at very high temperature. Okay, so NOx formation takes place at very high temperature. So you want to keep the temperature lower to avoid the NOx formation. Okay, so there are some techniques which we call LTC, low temperature combustion. So the purpose of those low temperature combustion techniques is that we want to reduce the combustion temperature, so there is less NOx formation. But you know that at lower temperatures the HC formation will be higher. Okay, so there can be some unburned hydrocarbons, so they can result in HC formation. So in diesel engines mainly, there is always the trade-off between NOx and HC. If you want to reduce the HC, then you want higher temperature, but at higher temperature NOx formation will be more. And if you want less NOx formation, then you will have to keep the temperature lower, but at lower temperature HC formation will be more. Okay, so this is sometimes called NOx, uh, soot NOx trade-off. Okay, so yes, this NOx formation takes place when the flame temperature is very high. So this is true. Okay, okay. So if you want to reduce the NOx formation, then somehow you will have to keep the temperature little lower. And to keep that temperature lower, there are many techniques. For example, there is something called EGR, exhaust gas recirculation. So you are sending the exhaust gases inside the chamber, combustion chamber, inside the cylinder. So that will, because of that, there will be you know less temperature or the reduced temperature. And there are some other techniques that are called LTC, low temperature combustion techniques. So main purpose of all those techniques is to reduce the NOx and simultaneously reduce the soot. So we want to somehow eliminate this soot NOx trade-off. Okay, we will move to the question number 8. Question number 8, let us read this. It says that a Morse test is conducted or a 4-cylinder petrol engine, okay, at a rated speed of 2800 rpm with net brake load of 160 newton. Okay, the cylinders of the engines are cut in order of 1, 2, 3, 4 with their corresponding brake loads of 110.8 newton, 106.5 newton, 104.2 newton, and 110.2 newton respectively. Answer the following questions. The indicated load in newton and mechanical efficiency of the engine is how much? We have to find what? The indicated load and the mechanical efficiency. Okay. So first, let us try to understand what question means. So Moore's test is basically a test or experiment to find the indicated load or the indicated power. So indicated power, we have discussed in some previous session that whatever power you are calculating from indicator diagram or the PV diagram, that is indicated power. But that is not the power which you are getting at your shaft, because some of the power is lost because of the friction. Okay. So indicated power minus friction losses is equal to brake power. That is what you are getting at the shaft. Okay. So if you want to, measure the power, how much, torque you are getting. So you will have to, apply or use some instrument at the shaft. But whatever those instrument will measure, that will be your brake power. Okay. That will not be the indicated power, right? But if you want indicated power, then somehow you need the information about the frictional losses, right? So indicated power will be equal to the brake power plus friction losses. Okay. But at the shaft, you will be getting only brake power. And that is what will be measured by your dynamo. Okay. Dynamo is basically an instrument which measures the torque. Okay. And if you know the, RPM, then you know the power. Okay. So somehow you need the information about frictional losses. Okay. So how does this test work? So this is actually for more than one cylinders. So what will happen? Let us say there are two cylinders. Let us take the simpler example. Cylinder 1 and cylinder 2. Okay. When both of these cylinders are connected to shaft and when both of these cylinders are working, so at shaft, what will you get? You will get brake power of cylinder 1 engine, the cylinder 1 plus brake power from cylinder 2. Okay. Now let us say you cut the fuel supply to the cylinder 2. Okay. Let us say there is no fuel supply in cylinder 2. So what you will get? You will get brake power from cylinder 1. Okay. But cylinder 2 will still apply the frictional losses, right? So in the first case, when both of these cylinders were running, then you are getting indicated power of cylinder 1 plus indicated power of cylinder 2 minus frictional losses of cylinder 1 minus frictional losses of cylinder 2. Correct? This is when both cylinder firing. Okay. But if you cut the supply of, cut the fuel supply of cylinder 1, sorry, cylinder 2, then you will get how much? You will get indicated power of cylinder 1, but not the indicated power of cylinder 2 because there is no, fuel supply. But cylinder 2 will still contribute in frictional losses. Similarly, when you will cut the supply of fuel supply of cylinder 1, you will get indicated power from cylinder 2, but you will still get the friction losses from cylinder 1. Correct? When you cut the fuel supply of cylinder 1, then you will get indicated power from cylinder 2, but friction will be there in both the cylinders. Okay, so from these equations you can find the friction losses, correct? So let us say equation 1, this equation 2, this equation 3. Okay, so if you want indicated power of cylinder 1, let us say, then you just subtract equation 3 from equation 1, correct? So you'll get IP1. And if you want the indicated power of cylinder 2, you just subtract equation 2 from cylinder 1, correct? Okay, so if there are more than two cylinders, then still the same concept is used, and in this manner you can get the frictional losses as well as as well as the indicated power. So in this question there are four cylinders. Okay, four cylinders, and speed is given 2800 rpm, and the net brake load, this is the total brake load of 160 newton. Okay, so when these cylinders are cut in this order, uh, 1 2 3 4, then this is what you are getting. Okay, first, so here we have four cylinders. Okay, so cylinder 1, cylinder 2, cylinder 3, and cylinder 4, and of all of these cylinders are connected to one shaft. Okay, so when you cut the fuel supply of cylinder 1, then whatever power you are getting, that power will come from these remaining three cylinders. Okay, so if you subtract this torque from the initial torque, then you will get the indicated torque of first cylinder. Okay, so if you want to indicated torque, indicated torque of cylinder 1, it will be how much? 160 minus 110.8 newton. Cylinder 2, it will be 160 minus 106.5. 3. Similarly for cylinder 4, 104.2 and 110.2. Okay, okay, so we have to find the total indicated load. Okay, so to find the total indicated load, we just add all these loads, individual cylinder loads. All these are the indicated load of individual cylinders. So if you add them all, then you will get 4 into 160 minus 1110.8 minus 106.5 minus 104.2 minus 1110.2 Newton. Correct? So I will just use my calculator to calculate this value. So 4 into 160, it is 640 minus 1110.8 minus 106.5 minus 104.2 minus 1110.2. So it is coming out to be 208.3. Okay. Okay. So this is the total, indicated load. And we have to find what? Mechanical efficiency. So mechanical efficiency is defined as brake power divided by indicated power. Okay. Or in terms of load, you can write it as brake load, you can say, divided by indicated load. Okay. So this value will be less than 1 because there are some frictional losses. Okay. So brake load is it basically indicated load minus frictional torque, or just let us say frictional load, divided by indicated load. So you get 1 minus frictional load minus indicated load. So here you can see that this mechanical efficiency is less than 1 because you are subtracting these frictional losses. Okay. So I hope you can calculate this value. The brake load, how much is the brake load? Brake load is 160 Newton. 160 Newton. Okay, I am just substituting this in this formula. 160 Newton divided by indicated load, that is 208.3. Okay, so how much we are getting? 160 divided by 208.3. So we are getting 0.768. So that is 76.8%. Okay. Okay, so around you can say 23% is lost in the friction. Okay, so there is a lot of friction. Okay, so how much is lost in friction? 100 minus 73.8. So it is around 23.2% is frictional loss. Okay, so anyway, we had to find this value and this value. So there are four options: option A, B, C, D, and values given in option A are the correct. values. Okay, so correct option is option A. Okay, so I hope that this Morse test is clear. How does this test work? How do we find equivalent, indicated power? How do we find frictional losses and brake power anyway you find from the dynamo? Okay, dynamo basically measures the torque. So there are some load cells. Load cells will, tell the load, how much load is there and at what distance those loads are applied. So from distance and force, the torque, and from torque and RPM, the power. Okay, so power is basically torque into, you know speed, tau into omega. uh, okay, so I hope this question is clear, and we can move to the question number 9. Okay, okay, question 9. It says that the possible cause of hydrocarbon emission is non-stoichiometric air fuel ratio, incomplete combustion, or wall overlap. So as we discussed in some previous question, there is some soot particles, some unburnt hydrocarbon in the exhaust. And what is the, you know region of those HC emissions that we have to tell? So HC is basically unburnt hydrocarbon. So unburnt means there is not the complete combustion. So incomplete combustion, of course, this is the correct option. But the reason behind this incomplete combustion can be there is a lot of fuel and less air. So you can say non-stoichiometric air fuel ratio. This is also the correct option. And wall overlap means that there was not the complete, exhaust taken place, and there was some, intake air was coming, but there was some exhaust left inside the cylinder, so that might have been mixed with the intake air. So that can be one reason. So wall overlap is, also a possible cause of, HC emission. So this valve timing, the closing of valve, the opening of valve, these timings are very important, and these are very difficult to adjust, especially in, you know this cam type of systems. Okay, because they are mechanically controlled. Okay, so all of these correct options. So part D should be the correct option, all of these. Okay, so I hope this is clear, and we can move to the next question. Question number 10 says that during idling condition of the vehicle, idling means that when you are not, running your vehicle. For example, you just uh, rotate your key, or just standing. Okay, you are not running your vehicle. That is called idling. Okay, so in idling, there is no applied load, only frictional losses are there. So in idling, the engine is working just against the friction. Okay, so during the idling condition, the NOx emission in CI engine will be lowest. So you have to tell whether it is true or false. So we have discussed in some previous question that NOx the NOx formation takes place at very, very high temperature. So when the temperature will be high, there will be more NOx formation. When the temperature will be less, so there will be less chance of NOx formation. So in idling condition, the temperature will be less, right? Because you are just, standing. You are not applying any extra load. You are just working against the friction. So because the temperature will be less, so there will be less NOx formation. Okay, so yes, it is true. During the idling, the NOx formation will be very low. It will be lowest actually. So option should be true. Okay, I hope this is clear, and we can move to the next question. Question number 11 says the knock in diesel engines occur due to. So this we have already discussed in some previous question, but anyway, let us see it again. The instantaneous auto ignition of last part of charge. Part B says reduction of delay period. Part C says delayed burning of first part of the charge. Option D says instantaneous burning of the first part of charge. Okay, so we have discussed that when you start injecting the fuel inside the chamber, it is not immediately burning. Okay, so there is some delay that we call ignition delay. After that delay period, this pre-mixed, okay, pre-mixed means whatever fuel you have injected and that fuel have mixed with air, so that pre-mixed you know pre-mixed part of fuel that will suddenly burn after this ignition delay period. Okay, so if you have injected a large quantity of fuel before the ignition start, then there will be sudden combustion, sudden pressure and temperature rise. And if you have injected very less quantity, so there will be not much rise in temperature or pressure. Okay, so instantaneous auto ignition of last part of charge, no, it is not the correct option. Reduction in delay period, no, reduction in delay period can be used to eliminate the knock that we have discussed in some previous question. Part C says delayed burning of first part of charge. Yes, it is the correct statement, because delayed burning of first part of charge will lead to formation of large quantity of premixed charge, so that will suddenly burn and that can lead to knock. So part C is correct option. And part D says instantaneous burning of first part of charge. No, it is not the instantaneous. There is some ignition delay. Okay. So delayed burning of first part of charge will cause the knock in diesel engine. Okay. So if you want to reduce the knock, you should either try to reduce the delay. That can be difficult to control, but fuel control, the controlling the quantity of fuel injection, that is easier nowadays, because you are using you know electronic fuel injection systems, and that is quite easy. Okay, so you inject very less quantity of fuel during this delay period, and after the delay period you can inject whatever is required. Okay, so yes, delayed burning of first part of charge can cause knock in diesel engines. Okay, so we will move to question number 12. Question number 12 says the carbon spares are generated in the combustion chamber in fuel rich zones where there is not enough oxygen to convert all carbon to CO2. So, yes, we have discussed this thing in some previous questions, that incomplete combustion can be there because of lack of oxygen. Okay, so when fuel is injected, it comes out as a spray, and that spray is basically some droplets, and droplets undergo some breakdown. They will break down into smaller droplets. Those droplets will evaporate and they will get mixed with air, and that will burn. Okay, so this is, let us say, our spray. And you know that inside, or you can say near the core of this spray, there will be large quantity of fuel. Okay, and outside the spray there is air, and inside the spray there is fuel. So somewhere in between there will be stoichiometric zone. Okay, and outside the stoichiometric zone there will be you know excess air, or you can say less fuel, or you can say lean region, or here it is fuel inside the core, near the core it is fuel rich region. Okay, so near the core there is fuel rich region, there is less air. So okay, so they're not the complete combustion, and that will lead to formation of these carbon spares. Okay, so the carbon spares can be formed near this fuel rich region or the core region. Okay, so here in this region there will be very very high temperature. So this is NOx formation will be near to this zone, and HC formation or carbon sphere formation will be near the fuel rich region or the core region. Okay, this is our spray. Okay, so this is true. The carbon spares are generated in the combustion chamber in the fuel rich zones where there is not enough oxygen to convert all the carbon to carbon dioxide. Okay, fine. So we will move to question number 13. Question number 13 says the spark plug is fired at 18 degree before the top dead center BTDC in an engine running at 1800 rpm or revolutions per minute. It takes 8 degrees of engine rotation or crank rotation to start combustion and get into flame propagation mode. Okay. The flame termination occurs at 12 degree after the top dead center ATDC. The bore diameter is 70 millimeter and the spark plug is 8 mm offset from the center line of the cylinder. We have to find the effective flame speed. Okay. So you have studied that there are mainly, three stages of combustion in an SI engine. Okay. So first there is, start of ignition because of, spark. Then there is flame propagation mode, and then there is flame termination mode. Okay. So this spark plug action takes place few degrees before the top dead center, and then uh, after that there is ignition mode. Okay, the develop of flame kernel. Then there is flame propagation mode, and the flame will terminate after a few degrees after the top dead center. Okay, so spark plug is fired. Spark takes place at 18 degree before the top dead center. Okay, and it takes 8 degree of rotation to start combustion. Okay, so start of combustion will take place 8 degrees after that. Okay, so that means 18 degrees minus 8 degrees is equal to 10 degrees before the top dead center. Okay, then flame termination occurs at 12 degree sorry, after the top dead center. So how much degrees the crank will rotate during the combustion or flame propagation mode, or you can say uh, angle, what to say, flame propagation angle, let us say. So how much is that? This is 12 degree ATDC minus 10 degree BTDC, or you can say 22 degrees. Okay, so this is the time, or in terms of angle, during which the flame propagates. Okay, we have to find the speed, and speed of what? Flame speed. Okay, and to calculate, we know to calculate the speed of anything, we need two things: we need distance and time. Okay, so dist this we have calculated 22 degree, and corresponding to 22 degree, or the time taken by shaft to rotate by 22 degree, we can calculate from this rpm. Okay, so at 800 rpm. So this means 360 in one round. There will be 360 into 800 per minute, right? So this much angle uh, the shaft will rotate per minute. Okay, so you can write 360 into 1800 divided by 60 per second. Okay, so this much angle shaft rotates per second. So to so time taken by shaft to rotate by 22 degree. So we have to find this time. Okay, so this will be equal to 22 degree divided by 360 into 1800 into 60, this much seconds. Okay, so we will just calculate this value. 22 into 60 divided by 360 into 1800. So it is coming 2 into 0 3 7 into 10 to the power minus 3 second, or you can say something like 2 millisecond. Okay, so within 2 millisecond the flame has propagated. Okay, the whole flame propagation process will take like something around 2 seconds. Okay, okay, the bore diameter is 70 mm. This is our bore, and bore diameter is 70 mm, and it is saying that the spark plug is 8 mm offset from the center line. Okay, so the spark plug is not at the center, it is something around something like here. Okay, let us say here it is a spark plug. Okay, so this distance is 8 mm. Okay, so flame will propagate from this spark plug from here to this side as well as this side. Okay, so we will take the uh, bigger side because flame have to cover the whole region. So the distance which flame has to travel is 70 by 2 mm plus this offset of 8 mm. So 35 mm plus 8 mm. So it is 43 mm. Okay, so we have the distance. Now you can calculate the effective flame speed. It will be equal to distance divided by time. So 43 mm divided by 2.073 into 10 to the power 3 second. Okay, or you can write it as 23 43 by 2.037 meter per second. Okay, so we will just calculate this value. 43 divided by 2.037, so it is coming out to be 21.11 meter per second. Okay, so let us check if there is any such option. uh, Part A is 23.5, part B is 21.08, part C is 25, and last part is 20. So part B is the closest option. Okay, 21.1, and our 21.1 is our answer, and here it is given 21.08. Okay, so part B should be the correct option. Okay, so I hope now you are able to calculate the effective flame speed, and for that you need to convert uh, the CAD value to the corresponding time value, and the vice versa. Okay, so this is very important because uh, most of the time the values will be given in CAD angle. Okay, like before TDC this much degree, after TDC, and so on. So you need to convert all those angle values into corresponding time, then you can proceed to solve your question. Okay, so if this is clear, then we will move to the question number 14. Okay, question 14, it says that in a compression stroke there is which type of heat transfer to the cylinder wall, followed by combustion where peak temperature is of order of 3000 Kelvin. Okay, so the heat transfer can take place either by convection or radiation or conduction. So heat transfer to the wall, that will take place by either by radiation or by conduction, because there is no solid medium, because inside the your cylinder there is some gases, hot gases. Okay, so from gases to cylinder wall there will be either radiation or convection. Okay, so radiation takes place at very very high temperature. Okay, but here this is being asked that heat transfer mode in compression stroke. So compression stroke means that gases are being compressed and the temperature of gases is being continuously increased. Okay, but there is no combustion has taken place. Okay, so it is before the combustion stroke. So the temperature is not that much that you should consider the radiation. Okay, the radiation mode of heat transfer, that is significant only when there are very very high temperatures. Okay, and the high temperatures occur only after the combustion. Okay, but in the compression stroke only convective heat transfer will be dominating mode. Okay, so part A is the correct option. So you can read it again. In compression stroke there is convective heat transfer to the cylinder wall, followed by combustion where peak temperature is of order of 3000 Kelvin. Okay, so it is written that followed by combustion. Okay, when the peak temperature will reach around 3000 Kelvin, then after combustion you should also consider the radiation, but before the combustion only convective heat transfer will be the dominating mode of heat transfer to the cylinder walls. Okay, so yes, uh, convective heat transfer should be the correct option. So I hope this is clear. Okay, so we will move to the question number next question 15. Question number 15 says in SI engines or spark ignition engines, the maximum flame speed is obtained when the equivalence ratio is. Okay, so we know that flame speed depends on equivalence ratio. Okay, and if you have watched the lectures, then you might have find this type of graph. On y-axis there will be flame speed, and this flame speed is the function of equivalence ratio. And you might have found this type of curve. So there is some maximum flame speed. Okay, so if you go, I mean, either left or right to this value of equivalence ratio, then your flame speed will be reduced. Okay, so at some specific type, I mean a specific equivalence ratio, you will get maximum flame speed. But I will not answer this question because probably this question is in the assignment as well. So I will request you to just go through the lecture and you will find this type of graph, and from there you can easily answer this question. But I can just give you a hint that uh, when there is excess air, or you can say when there is a lean mixture, then the flame speeds are less, and flame speeds are maximum when there is some extra fuel. But that fuel should not be very very extra. Okay, if you increase this fuel quantity to, more than some limit, then again the flame speed will be reduced. Okay, so there is some range where you get the maximum flame speed, so you have to tell that range. Okay, so you can check this in the lectures. So this is from assignment. Okay, so you can check this in lectures. Okay, so this is not very difficult to answer if you just quickly go through the lectures. You can easily answer this. Okay, we will move to question number 16. So you have to find this range. Okay, question number 16 says that with increase in the speed of a SI engine, the crank angle required from flame propagation is affected or not affected, or what? Okay, we know that when you increase the speed, the turbulence increases. Okay, so with the increased turbulence, the flame speed will increase. Okay, so ideally the crank angle required for our flame propagation, that should reduce, but that effect is not that significant. Okay, so most of the time we are neglecting that dependence. Okay, so we most of the time we assume that this crank angle required from propagation is almost independent of increasing speed. Okay, so there is very very less dependence. Okay, so whatever crank angle was required at lower speed, so almost same crank angle will be required for flame propagation at higher speeds. Okay, so either you can say it is true or false, but as per lectures you can say it is false. Okay, because that is almost unaffected. Okay, so okay, so this was the last question. So I hope that all these questions are clear. We can just quickly see. We have seen the effect of octane number on the ignition delay. We have discussed the stoichiometric fuel air ratio, and we have discussed the equivalence ratio. We have discussed the brake specific fuel consumption and how to find the efficiency. Then we have seen what is meant by engine capacity. Engine capacity is basically total swept volume. Then we have seen that in diesel engine, during the ignition delay period, whatever fuel is injected, all that fuel will burn very quickly, so that can lead to knocking. To eliminate that knocking, either you should inject very less fuel during the ignition delay period, or you should try to reduce the ignition delay. Okay, and we seen that there is some unburnt hydrocarbons in the exhaust, and the concentration of those HC. We discussed that NOx formation takes place at very high temperature, and the mechanism responsible for that is called Zeldovich mechanism. Okay, then we discussed Morse test. Morse test is basically to find the indicated power or frictional losses. Okay, and the brake power can be found from dynamo, which basically measures the torque, and if you know the RPM, multiply the torque by angular speed, you will get the power. And HC emissions are because of unburnt fuel, and that can be because of lack of oxygen or valve overlap. Okay, and during the NOx formation takes place at very high temperature. So during idling there is not that much high temperature, the temperatures uh, are little less, so there will be less NOx formation during the idling. And knock in diesel engine again, okay, this is because of delayed burning of first part whatever have been injected before during the ignition delay period. So that whole charge, premixed charge that will burn suddenly, that can lead to NOx formation and knock and noise. Okay, and carbon spares are generated in combustion chamber in fuel rich zones where there is not enough oxygen. We have seen that there is different reason, uh, locations in the spray, like near the core of the spray, near the center line there is fuel rich region, there is less oxygen, so there will be more HC and carbon spare formation. And very very far from the spray there is uh, air, so there is lean region, and somewhere between this fuel rich and lean region there is you know stoichiometric region, there will be very very high formation of NOx. Okay, then we saw how to calculate this effective flame speed. We saw how to calculate this angle into corresponding time value, and then find the effective flame speed. Then we discussed that heat transfer from cylinder walls to heat transfer from the gases inside the cylinder to cylinder walls can take place either by a radiation or convection. And radiation takes place, radiation is significant only at higher temperature, but at lower temperature you can ignore the radiation. And at lower temperatures occur when there is no combustion or before combustion. So during that low, I mean, so before combustion, only convective heat transfer is significant. Okay, then we discussed that flame speed depends on equivalence ratio. Okay, when the equivalence ratio is less than 1, then there is less flame speed. Also there is some I mean range in which the flame speed is maximum, that you have to find from the lecture. And we discussed that crank angle required from flame propagation in SI engine is almost unaffected with speed of an SI engine. Okay, so that is what all for today. Okay, so I hope these questions were clear to you, and I hope that these questions will help you in solving your assignment. And whatever doubt you had, I hope some of them, at least some of them, might have been cleared. So we will stop here and we will meet in the next session. Okay, thank you.